Hello, everyone. Welcome to the ninth lecture of AAE 301. In this lecture, you will learn how to analyze a linear time invariant system through its transfer function. As always, let's start with an overview of the lecture. We will start with an introduction to linear time invariant systems, or LTI systems. These systems are commonly seen in various engineering applications. Next, we will delve into the transfer function of an LTI system. The transfer function of an LTI system provides valuable insights into the system behavior, such as the bounded input and bounded output stability, or BIBO stability of the system. Finally, we'll discuss the final value theorem. This theorem allows us to determine the output of a BIBO stable LTI system when it is subject to a step input. Okay, now let's get into the details. First, what is a system? A system is a mapping from an input signal or forcing function u of t to an output y of t. Graphically, we can draw a block diagram to show the relationship between a system and its input and output. In a block diagram, the system is typically represented by a block. The output u of t is represented by the arrow pointing inward to the system block, and the output y of t is represented by the arrow pointing outward from the system block. An example of a system is the mass spring damper system. In this lecture, I will use this system to illustrate several important concepts. So let's take a closer look at the system together. This system is composed of three components: a brick with mass m that can move horizontally on the ground, a spring that is attached to the wall and the mass brick with the spring constant K, a damper that is attached to the wall and the mass brick with damper constant C. Thus, the name of the system is called the mass spring damper system. Now, the input to the system is the horizontal force exerting on the mass, denoted as U of t, and the output of the system is the horizontal displacement of the mass brick from the wall, denoted as y of t. Here, I've drawn a block diagram to serve as an abstraction of the system. All right, that was an introduction to a system. Now, let's take a look at what is a linear time invariant system, or LTI system. An LTI system is a system whose input and output relationship satisfies the linearity and time invariance properties. First, let's clarify what it means by linearity. Here, linearity means the relationship between the input and the output is a linear mapping. Imagine we have a system, and when it's subject to input u1 of t, the corresponding output is y1 of t. Similarly, for input u2 of t, the output is y2 of t. Now, if the system is linear, the output resulting from alpha times u1 of t plus beta times u2 of t will be alpha times y1 of t plus beta times u2 of t. This means that for a linear system, the output resulting from an input, which is a linear combination of different input signals, will be the same linear combination of the outputs associated with those inputs. Now, let's clarify what it means by time invariance. Here, time invariance means that if we apply an input to the system now or t seconds from now, the output will be identical except for a time delay of t seconds. Again, to help you better understand, imagine we have a system, and when it's subject to an input u of t, the corresponding output is y of t. Now, if the system is time invariant, the output resulting from a delay copy of u of t will be a delay copy of y of t. This means that for a time invariant system, whether we apply an input now or later, the output remains identical, just with a slight time lag. So in summary, an LTI system is a system whose input and output relationship satisfies the linearity and time invariance properties we've just seen. Before I wrap up the introduction of LTI systems, I'd like to mention that a LTI system is typically described by a linear constant coefficients ordinary differential equation, or LCC-ODE, along with a set of initial conditions. A LCC-ODE for a system can be obtained by physics laws such as Newton's second law, and is typically in the form of the equation shown here. As you can see, there are no nonlinear terms in the equation, and the coefficient of each term is constant, which is why this type of ODEs is called linear constant coefficient ODEs. In addition, when all initial conditions are zero, the systems described by LCC ODEs are LTI systems. Okay, we've looked at the LTI systems. Now let's learn how to analyze an LTI system through its transfer function. The transfer function of an LTI system is a function g of s in the S domain that describes the input-output relationship of the system, and it is defined as the fraction ys over u of s. Here, y of s is the Laplace transform of the output y of t, and u of s is the Laplace transform of the input u of t. According to the definition of the transfer function, if we multiply u of s on both sides of the equation, we see that y of s is the product of g of s and u of s. Now, recall that the product of two functions in the S domain is equivalent to convolution between the inverse Laplace transform of these functions in the time domain. Therefore, if we call the inverse Laplace transform of the transfer function g of t, then the output of the system in the time domain y of t is simply the convolution of g of t and the input u of t. Now let's take a deeper look at g of t. When a delta Dirac function or an impulse function delta of t is applied to the system, the output y of t is the convolution between g of t and delta of t. Then, according to the definitions of convolution and the impulse function, we can see that the convolution between g of t and delta of t is simply g of t itself. In other words, the output of an LTI system when the system is subject to an impulse function will be g of t, which is the inverse Laplace transform of the transfer function. And for this reason, g of t is called the impulse response of the system. In addition, if the impulse response g of t of the transfer function g of s of an LTI system is known, then the input-output relationship of the LTI system can be captured. Therefore, an LTI system can be characterized by its impulse response g of t or transfer function g of s. Now, let's take a look at some examples of how to obtain the transfer function of an LTI system described by a LCC ODE. In the first example, the system is given by y triple dot plus 8 times y double dot minus 3 times y dot plus 2 times y equals to 4 times u. Now, to find the transfer function of the system, we apply Laplace transform to both sides of the equation and set the initial conditions to 0. Then we will get s cubed times y of s plus 8 times s squared times y of s minus 3 times s times y of s plus 2 times y of s equals to 4 times u of s. And we can simplify the equation as s cubed plus 8 times s squared minus 3 times s plus 2 times y of s equals to 4 times u of s. Now, recall the transfer function g of s is defined as the fraction of y of s over u of s. Thus, we see that the transfer function of the system is given by 4 over s cubed plus 8 times s squared minus 3s plus 2. In the second example, we will find the transfer function of the mass spring damper system. According to Newton's second law, the equation of motion of the system is given by m times y double dot equals to u minus k times y minus c times y dot. And if we move all the terms related to the output y of t to the left-hand side of the equation, we will get the LCC ODE m times y double dot plus c times y dot plus k times y equals to u. Now let's find the transfer function of the system. Again, we apply the Laplace transform to the both sides of the equation and set the initial conditions to 0, then we will get m times s squared times y of s plus c times s times y of s plus k times y of s equals to u of s. And we can simplify the equation as m times s squared plus cs plus k times y of s equals to u of s. Now recall the transfer function g of s is defined as the fraction of y of s over u of s. So we can see that the transfer function of the system is given by 1 over m times s squared plus c times s plus k. And we can divide the numerator and the denominator by m at the same time to make the denominator polynomial monic. And in the end, we will get this expression here, which is 1 over m over s squared plus c over m times s plus k over m. And this is the transfer function of the mass spring damper system. Okay, we've talked about how to obtain the transfer function of an LTI system described by a LCC ODE. Now let's take a look at how we can analyze an LTI system by its transfer function. Specifically, we will check whether an LTI system is bounded input, bounded output stable, or BIBO stable. Here we say a system is BIBO stable if its output to any bounded input is bounded. This condition can be mathematically expressed as follows. If the magnitude of the input is bounded above by a constant Umax all the time, then the magnitude of the output should be bounded above by a constant Ymax all the time as well. Now let's learn how we can determine whether an LTI system is BIBO stable. First, note that an LTI system is BIBO stable if and only if all the poles of its transfer function g of s have negative real parts. Therefore, to check whether an LTI system is BIBO stable, we only have to check whether the poles of its transfer function are in the open left half plane. Okay, now let's take a look at an example. In this example, we will check whether the mass spring damper system is BIBO stable. First, let's recall that the transfer function of the system is given by g of s equals to 1 over m over s squared plus c over m times s plus k over m. And the poles of the transfer function are the roots of the denominator polynomial, and they are given by negative c plus negative the square root of c squared minus 4 times m times k over 2m. Notice that the parameters m, c, and k are all positive, and we can show that when these parameters are positive, then the real parts of the poles are negative. Thus, we can conclude that the system is Peeble stable. Now, we can verify this result with a numerical simulation. In this simulation, the parameters m is equal to 1, c is equal to 0.5, and k is equal to 1. The input to the system is a sinusoid, sine of t, whose magnitude is bounded above by 1. Here I have a plot that shows the input and the output of the system over the time interval from 0 to 50 seconds. The input is represented by the blue line, and the output is represented by the orange line. From this graph, we can see that the output is also a sinusoid, whose magnitude is bounded above by 2 at all times. The bounded output when the system is subject to a bounded input is exactly what we have expected since the system is Peeble stable. Now let's take a look at the second example. In this example, we will check whether a mass spring system is Peeble stable. First, notice that the transfer function of the mass spring system is the same as the one of the mass spring damper system, except that the damping constant C is equal to 0. Similarly, the poles of the transfer function are the same except that C equals to 0 for the mass spring system. Therefore, the transfer function of the mass spring system is given by G of S equals to 1 over m over s squared plus k over m. And the poles of the system are plus negative I times the square root of k over m. And here I like to note that the value square root of k over m is called the natural frequency of the system. Obviously, the real parts of the poles are 0 for any positive values of k and m. So the mass spring system is not Peeble stable. Again, let's verify this result with a numerical simulation. In this simulation, the parameters and the input are the same as the previous example, except that the damping constant C is equal to 0. Here, the graph shows the input and the output of the system over the time interval from 0 to 50 seconds. The input is represented by the blue line, and the output is represented by the orange line. From this line, we can see that the output is a sinusoid whose magnitude grows exponentially. In fact, this phenomenon has a name called resonance. And this happens because the system is subject to a sinusoidal input with frequency equals to the natural frequency of the system. From this simulation, we see that the output can be unbounded even when the input to the system. From this simulation, we see that the output can be unbounded even when the input to the system is bounded. And this matches our previous conclusion that the system is not Peeble stable. Okay, let's wrap up this part with a remark. In the previous example, we've seen that the poles of the mass spring system are plus negative I times square root of k over m. And here, square root of k over m is called the natural frequency of the system. And when the system is subject to a sinusoidal input with frequency as the natural frequency of the system, a phenomenon called resonance will occur to the system and may lead to excessive vibration or even structural failures. This phenomenon results from the energy the system absorbed from the external input can be stored and easily transferred between two storage modes, such as the kinetic and potential energy without energy loss from cycle to cycle. On the other hand, for the mass spring damper system, due to the existence of the damper, which dissipates energy when the mass is moving, Energy loss will occur from cycle to cycle, and thus the output won't end up unbounded. Now, let's move on to the last part of this lecture, the final value theorem. The final value theorem is an important result for a Beeble-stable LTI system. This theorem allows us to compute the final value of the output of a Beeble-stable LTI system when the system is subject to a step function as an input. Specifically, when the input is a scaled step function with a scaling constant U0, the final value of the output will be the product of the static gain of the system G of 0 and U0. Now let's apply this theorem to compute the final value of the output of the Beeble-stable mass spring damper system when it is subject to a step input with scaling constant U0 equals to 2. According to the theorem, we know that the final value of the output is equal to the product of the static gain and the scaling constant. In this case, the static gain G of 0 equals to 1, and the scaling constant is 2. Therefore, the final value of the output is 2. And let's verify this result with a numerical simulation. Here is a graph that shows the input and the output of the system. The input is represented by the blue line, and the output is represented by the orange line. And you can see that the input is a step input with a scaling constant equals to 2. And the output converges to 2 as time goes on, which matches our previous analysis. Okay, this is the end of today's lecture, and I'll see you in the next one.